Hello everyone, today we are going to learn about junction field effect transistors, JFET. Junction field effect transistors was first theorized by Julius Edgar Lindenfield in 1926-1928, and the first patent on any junction field effect transistor was by Henrik Welker, who patented it in 1945. Now, why do we learn about JFETs? What are the uses of JFET? Because before learning about anything, we have learned so much in our schools and various places, but we do not know application. Whenever it comes to any question regarding practical applications, we get stuck on them because we do not have a clear idea why we are learning. So before telling you about what a JFET is, what it can do, and how it operates, I am first going to inform you about what are the many applications of JFET. Now the first application is as a switch. As a switch, we already have so many mechanical switches. We use switches in our rooms and we have never seen any JFET. A switch is a very simple device, as we have learned in our lower classes. A switch is basically this, a open circuit, and if we want a switch, we can basically have two metal plates. Whenever they leave contact, it becomes a switch and it's open circuit. So why JFET? How does JFET help us in switching? Now the reason why JFET is used as a switch is not so that you can control your lights and fans. Inherently, switches are mechanical devices that move, and any device that moves, no matter how small the movement is, will break. And any device which does not have any moving parts is gonna outlast it very easily. So JFETs are devices which can switch the current on and off without actually moving. They can make and break the circuit without moving, and that is a very big benefit in terms of JFET used as a switch. Also, we can make very small JFETs, but we cannot make very small switches on the same scale as JFET. So they can last incredibly long and also be incredibly small compared to a more traditional switch. Our second use would be that as an buffer amplifier. What is a buffer amplifier? Well, basically, whenever you are speaking into mic, we all know that there is some sort of a diaphragm in the mic and it moves as you speak, and that generates some electrical pulses which are used to interpret your voice. But don't you think that our speaking does not actually produce voltages in terms of volts? It's more like millivolts or microvolts, and that is a very small signal to be carried all the way from a small microphone to a big speaker. It's gonna get distorted a lot. So in those cases, we use JFETs as amplifiers to amplify that signal and make it easier for people to understand, for our equipment to understand that signal. Third, we can also use JFETs as voltage controlled resistors. These are usable in applications which require adjustable resistance, such as volume control and automatic gain control circuits. Also, these JFETs can be used as low noise amplifiers and oscillatory circuits, cascade amplifiers, and I have so many other uses. That is why we learn about JFET. Now we'll come to the actual working, what's going to be asked in your examinations. That is very important for us. Okay, so this is how a JFET looks like. Okay, we have got a gate, a drain, and a source. Now all three of these have been named logically, and I'm going to explain the logic behind their names in a short while. First, you might be noticing that there are some black things near the drain. Okay, this black thing, this is a metal contact point. Okay, this is nothing but a metal contact point. Okay, this metal contact will help for the current to be conducted through this channel which you can see here. This is an N-type channel. Basically, JFETs come in two flavors. There's the NPN and there's a PNP, or more commonly these are known as N channel and P channel. The channel refers to this area which basically provides a channel for the numerous electrons which are going to flow from the source to the drain. Now that I have said that the electrons are going to flow in this direction, what would be the direction of the current? The current flows in this direction. So the current flows from drain to source, from which we can predict the voltages at which we have to maintain the drain and the source. Now, as we know, current flows from a region of higher potential to a region of lower potential. So in a JFET circuit, the drain is always kept at a higher potential and the source is kept at a lower potential. We will call this VDS. Okay, now the second thing is this gate which you can see here. Now, as you might have inferred from the name, this is the part which is going to control the flow apart from drain and source. Of course, if you will apply higher voltage across drain and source, the current passing through will become higher. But this is the part which is going to open and close in a virtual sense and make it and make or break the circuit. How will it work? I'm going to explain. What we do is we have a battery. Okay, wait a minute. Yeah, we have something, a battery, a potential applied to this. Okay. Now, in lower classes, we have studied up something about diodes. Okay, these are basically PN junction diode which we have studied. What happens when there's a P-type and N-type material side by side? What happens is that a small depletion region is created, and because of this depletion region, the current flow ceases. Something very similar is going to happen here. These two P-type parts, a junction, it's basically, see, a JFET is basically a N-type like silicon bar that has two P-type diffuse materials here and here. Okay, so what happens is that the drain is maintained at a higher voltage, okay, and these P-type parts, they are given a voltage. We give a potential difference across gate and source. We will call it VGS. Okay, this potential is what controls a JFET. That is also why they are known as voltage control devices, because the voltage controls. Earlier we have read about BJT, bipolar junction transistor, which are current control devices, because they are controlled by current. You control them by varying the amount of current. But here we are going to be varying the amount of voltage we provide to between the gate and source, and that is going to control our flow of electrons or our current. What will happen basically is we are going to reverse bias this junction between the P-type and the N-type material. By reverse biasing this junction, now already just because this junction is here, this part is here, we already have a depletion region, something like this, and as we all know, electrons don't flow through the depletion region. Okay, so if we apply a VDS between the drain and source, the electrons are gonna flow here. Okay, they are gonna flow here. Now, to stop the flow of electrons, what we need to do is we need to make it such that the depletion region becomes something like this. As you can see, it's almost closed. There is almost no gap left for the electrons to pass through. This will break the circuit. How it is done? Now going back to our diode for a second, we know that if we connect the P part to the negative terminal of a battery and the N part to the positive terminal of the battery, the depletion layer starts to expand. It starts to become bigger to prevent the flow of electrons. Same, we are gonna do this. It's essentially two diodes placed, like two diodes here. These are two diodes. There's nothing new. Okay, these are just two diodes. Making it took 10, like 15 years, because making this is hard, but thinking about it is not that hard. Okay, yeah. So how are these diodes gonna work? Okay, so here we have these two P parts. Okay, and now we are going to apply a negative potential here, and the source is gonna have a positive potential. Okay, what's gonna happen because of that? The depletion region, now the source is also going to have a negative potential like this. Okay, the positive potential is going to be with the drain like this. Okay, now that we have reverse biased this junction, basically we are reverse biasing this junction, it's going to increase, the depletion layer is going to increase. Okay, it's going to increase, and the same thing is happening with this, because these two are connected. So this depletion layer is also going to increase, eventually cutting off the flow of electrons. But the increase in depletion layer is not going to be the same here and here. Like, it's not going to be the same on this side versus on this side. The correct depletion layer would look something more like this. No, it will look something like this. Okay, it's gonna expand more towards the top end and less towards the bottom end. Now why is it so? Like, it expands more here, but it's not gonna expand as much here. To understand that, we need to take an analogy of this. What analogy? We can think of this whole channel as multiple resistors together. So you can think like there are 4x resistors here. 1, 2, 3, 4. Okay. Now, as we know, voltage is whenever resistors are connected in series, voltage are divided among them. So the voltage here would be V by 4. If the voltage across this entire V ds is V, the voltage will be V by 4, then V by 4, then V by 4, and then V by 4. Okay, now what happens, let's say this is at this gate is at plus V0 volts. Okay, plus V0 volts. No, it is at minus V0 volts. Okay, it's at minus V0 volts. Now what will be the potential difference between this place, this gate, and this drain metal strip? The potential difference would be whatever, let's say V here and V0 here. So it's going to be V plus V0. Okay, at this point. So obviously, as the potential difference is higher, the depletion layer width will be higher. It will be larger. But let's say we come here at source. Now if we add all the voltages from this point to this point, we are going to notice that this is equal to V. That means the potential here is almost zero, or the potential difference here is, you can say, it's zero. Now what's going to be the potential difference in this part along this area, it's going to be V naught. V naught for this and 0 for this. So 0 minus V naught is equal to V naught. Okay, so the potential difference is going to be V naught, which means as the potential difference is lower in this part compared to this part, the depletion layer will also be smaller in this part compared to this part. And that is why the depletion layer tends to be something like this. It goes something like this. It goes something like this, but actually it never touches. Okay, the depletion layer never touches. I'm not able to draw it, but it goes something like this. And this is how a JFET operates. Okay, now in the beginning, before I started explaining everything, I told you that this part here is of N type material, this part, and these are of P type. Does that actually have any significance? Yes. Basically, JFETs, as I told earlier, come in two flavors, N channel and P channel. This is an N channel JFET. Why? The channel, this thing is made of N type material. We also have a P channel JFET, and both of them are represented by this symbol. This symbol over here is how we represent JFET. And N channel JFET has, this is the direction of current going into it, into the source, and a P channel JFET has current coming out of the source, because they are comprised of N channel and P channel. N channel has more electrons. Okay, so this current is shown inside, but in an ideal diode, Ig should be equal to 0. Thank you.